Assalamu alaikum everyone. Hope you are doing great. Today we want to focus and discuss about energy balance on reactive processes that is actually involved in the in chapter 9 of your textbook. Hope you can actually find this video useful to understand the material that I uploaded on Moodle, and come back to me anytime if you have any question or any doubt. So by actually knowing the course outline, I will review what we want to study in this video and in this week of a study. So first of all, I will review for you the energy balance on non-reactive processes that we did in the third week of a study, just for you to remember, because you need this part for this chapter. And then we will study we will actually study together some general point and introductory part of the this chapter 9 about reaction and reactive processes. Then we review the Hess law, and we come back actually to some terminology of the chapters. And finally, we will study more with some problems and showing you the solutions of those processes when there is a reactive process. So if you go back to chapter 8, we learn if we have a process that there is low values or negligible values of the kinetic energy and potential energy, or there is no kinetic energy or potential energy changes in the process, while there is no work, energy transfer in form of a work, we can reduce the energy balance equation to Q to heat equal to changes of internal energy for a closed constant volume system, and to Q equal to changes of internal energy for a closed system expanding or contracting against a constant external pressure. And finally, for it is the rate of heat transfer is equal to the changes of the rate of enthalpy changes for an open system at a steady state condition. So I provided for you the steps that you have to consider to solve or to actually to do the balance of energy on non-reactive processes. So we learned that if you want to calculate the internal energy, a specific internal energy or a specific enthalpy, when there is no table with ready available data, so we have to do some steps to provide and calculate these values. So I told you have to select the reference state first. This reference state should has a known phase, temperature, and pressure for each species involved in that process. Then we construct the path from the reference state to final state of the that component in the process, and we evaluate the transition in each steps. So as you know all the values, and if you remember, we provided an inlet-outlet enthalpy table. So we put all the data of the mole rate and specific enthalpy rate, and then it was easy for us to calculate all the delta H or actually delta U changes through using that table. And finally, we can substitute the values of delta H in energy balance form and calculate heat or heat rate or heat transfer rate. So to be able to calculate the enthalpy changes on from the reference state to the final state in the process, I show you how to calculate by using the changes of pressure, changes of temperature, and changes of phase transition. So if you remember, I asked you to use either to actually change either temperature or pressure or phase at once if you want to construct the path. So if there is changes of pressure at constant temperature, and for sure that there is no changes of the phase, you can, if it is solid and liquid, the changes of the enthalpy will be equal to V cap delta P, or a specific volume, multiplied by changes of pressure. And if your component is ideal gas or nearly ideal gas, or the gas with very low pressure to like some atmosphere, you can consider, you can actually neglect the changes of the enthalpy. For a process with changes of temperature, if it is at constant volume, you can use this equation, while if it is in the constant pressure, you can use this equation to calculate the changes of enthalpy at constant pressure and temperature change. And finally, if there was any phase change, while there was no temperature change, no pressure change, if there was conversion between solid and liquid, you have to use fusion heat. And if there is changes between liquid and vapor, means liquid to vapor or vapor to liquid conversion, you have to use evaporation heat. For sure, if the heat is positive, it is liquid to solid to liquid, and is negative if actually there is the other way. I mean, I don't mean negative or positive of the values. I mean a negative or reverse form of what you see in the table, or what you have as the delta HM or delta HV. So in your textbook, you have delta HM value and delta HV value in table B1, as I showed you in the previous session. That however, these values that is provided in table B1 is only for at 25 degree and 1 atmosphere pressure, and it's not, you cannot use them for other temperature and pressure. So this is what we learned so far, and I hope you can actually just remember what we studied in the third week of the study. So today we want to focus most on the reactive processes, when you have a reaction involved in your process. First of all, you have to understand that the amount of internal energy and enthalpy associated with chemical reaction are quite huge and large, and they are playing a major role in design and operation of chemical processes. So we have to consider how to calculate them to be able to do the energy balance on reactive processes. In this chapter, we learn how to calculate delta H, or actually for delta H, I mean changes of enthalpy rate for open system, or delta U and delta H for closed system. So once we have these values, as you know, we can refer to the energy balance equation or first law of thermodynamics and calculate other parts of the equation. Like for example, if it is heat, so we can calculate, as we discussed. So before that, I want to give you some definition of different points, like introduction part of this chapter. So we will go through some actually general points to be able to understand the final calculations. So first of all, I want you to know what is a heat of reaction. Heat of reaction is the enthalpy change when stoichiometric quantities of reactant at temperature and pressure are consumed completely to form product at the same temperature and pressure. So if the value is negative, the reaction is exothermic, and if the value is positive, it is endothermic. I want you to go to the book and study about these two terms to understand what does it mean, or remember, just because I'm sure you already know. What does it mean? Just to remember, what does it mean? Exothermic. Just for your own review, if the process or reaction is exothermic and delta HR is negative, it means that less energy is required to break the bond holding the reactant compared to the energy you need to break to form the products. So means in these types of process, you will the energy will be transferred. Actually, the energy will be released from the process when the reaction proceeds. This energy can maybe transferred from the reactor to the heat as heat, or it may serve to raise the temperature of the reaction mixture. However, when there is a positive amount of heat of reaction, means more energy is required to break the reactant bonds than the energy is released when the product bonds form. So leading to a net absorption of energy as the reaction proceeds. So before, actually, unless you provide this amount of the energy to the process or to the reactor, actually the process may not proceed or the temperature will be decreased. So this is actually the heat of reaction at the temperature and pressure. However, if this temperature and pressure are a specified reference temperature and pressure, they call it standard heat of reaction. So in our book, at least, it is 25 degrees and 1 atmosphere for this specified reference temperature and pressure. So they're showing like this way: when there is a standard heat of reaction, means when the temperature is 25 degrees and pressure is considered atmospheric pressure. So, so in that way, you will see when actually 1 mole of methane, 2 moles of oxygen react at 25, because it is actually at standard form, at 25 degrees, they will produce 1 mole of CO2 and 2 moles of water at 25 degrees and 1 atmosphere. By actually when this reaction proceeds, this amount of the energy will be released. Since it is negative, means that reaction is exothermic, and this amount of the energy will be released. So actually, for low pressure process, you can consider heat of reaction is independent of pressure anyway. So I just want to provide for you some general equations, how to calculate different parts of, how you will use these terms in your week of study. So first of all, the changes of enthalpy when you have the heat of reaction will be calculated through this equation. I want to tell you, as long as this heat of reaction as 25 degrees, this delta H is calculated at 25 degrees. So if you want to calculate delta H at other temperature, you cannot use these reactions. So if you are using delta H or at 25 degrees, this delta H can be calculated from this equation when the process or when the calculation was asked for 25 degrees or the same temperature as here. Heat of reaction, we will actually study how to calculate heat of reaction. So far, maybe in some process, they give you the heat of reaction as a known data. However, if it is not known, you have to be able to calculate it through either a standard heat of combustion or a standard heat of formation. What is this value? It is a stoichiometric coefficient, either for reactant or for product. We considered the value positive if it is a product, and we consider negative values if it is a reactant. So it is an equation. If you want to use, if you want to calculate standard heat of reaction from heat of combustion. If you have the information, or actually you want to use a standard heat of formation, you have to use this equation to calculate heat of reaction. So these two values, when we studied chapter 8, I told you how you can find standard heat of formation and standard heat of combustion in table B1. We will actually repeat it here. Zeta here is the extent of reaction that you studied before. It show actually it show how the reactor, to what extent the reactor proceeds. So you can calculate it if you have the mole of any of the, you can choose any of the component in your reaction, either reactive or product. So reactant or products. So that is known. You know how much the values at the end and at the beginning and at the final. So by knowing the values, that in two values, you can calculate zeta from either any of the components of the process that you have. And again, here is actually the stoichiometric coefficient of a specific component that you choose. And we actually use this law in our calculation all over this, in this chapter. So what Hess law tells us is say that if the stoichiometric equation for the reaction can be obtained by algebraic operations like multiplication, by addition or subtraction, on a stoichiometric equation of other reactions, then the heat of reaction can be obtained by performing the same operations on the heat of reactions. So it's better I show you in terms of some examples. Like here, we can see one type of actually Hess law application. The standard, not in this one, I mean in the examples that we are practicing now. The standard heat of combustion of N-butane vapor is given to you. Calculate the rate of enthalpy change if 2,400 mole per second of CO2 is produced in this reaction and the reactants and products are all at 25 degrees. So as long as it is the same temperature, we can use the equation I told you, delta H equal to zeta delta HR. So this equation is valid to use because the temperature of the process, or actually the temperature that we are asked to calculate the rate of enthalpy change is 25 degrees. So we need, we can use delta H equal to zeta delta HR, I mean the standard heat of reaction, and calculate the values of rate of enthalpy change. So for zeta values, we can use the data that is given to us. We know that 2,400 moles of CO2 is produced. There is no CO2 in the beginning, so the only values that we have in the outer stream, that is 2,400. So there is no inlet CO2, so it's considered zero. We have to go to the reaction and see what is the stoichiometric coefficient of CO2, which is 4. So we can actually calculate what is the extent of reaction, which is 600 mole per second, by knowing the extent of the reaction and available delta H, delta HR. We can calculate a rate of enthalpy change, which is this value. It was a simple process. In the other example, they ask us to, they give us the process equation. So they give us a reaction here. They ask us to calculate delta H, rate of enthalpy change, if 2,400 mole per second of CO2 is produced in reaction and the reactant and products are all at 25 degrees. So we need actually delta HR, or standard heat of reaction, to be able to calculate delta H at 25 degrees. What we know the standard heat of reaction of this process. So first of all, we have to look how these two reactors are, we have to compare these two reactors, reaction. So as you see, we have this reaction that is asked and this reaction that is given to us. What is the, if you compare these two reactions, what you will find out? This reaction is double of this reaction. I mean, if you double the stoichiometric coefficients, this reaction will be happen. So by knowing the, even the Hess law mentioned, if you actually do any changes of stoichiometric values by multiplication on a constant value, you can do the same changes on the heat of reaction. So since the reaction 2 is multiplication of the stoichiometric coefficient by 2, we can multiply the standard heat of reaction in this equation by 2. So it's just a simple thing, and I'm sure you already know about that. So we just double the heat of reaction, the standard heat of reaction for this known reaction by 2. This will be the heat of reaction of this process. So now the second terms that we need is extent of the reaction. We know 2,400 mole per second of CO2 is produced. There is no CO2 in the inlet. So the same way we use 2,400 mole per second of CO2 divided by stoichiometric coefficient of CO2 in this reaction, which is 8. So it will be 300. We use 300 multiplied by heat of reaction, the standard heat of reaction for reaction 2 that we calculate. It is again the same value. If you compare it with the previous calculation, you will see this is the same heat of reaction, because that one is the same reaction, right? And this value is kilojoule per mole. So now I hope that you understand so far. We have another example here. They ask us, they are giving us some information. The heats of vaporization of N-butane and water at 25 degrees is giving to us 19.2 and 44. What is the standard heat of reaction? Again, we are asked for a standard heat of reaction. Calculate delta H if the same amount of the molar or actually flow rate of CO2 is produced in reaction, and both reactant and product are at 25 degrees. Again, we are giving these the standard heat of reaction for this process. So again, we have to compare these two processes together, the one that is known and the one that is unknown. By comparing these two reactions, we will find everything is same. The only difference between these two reactions is the phase of H2O and N-butane. So what we can do, this is the information that is given to us, evaporation heat for N-butane at 25 degrees and for evaporation heat of water at 25 degrees. So I know these two reactions are same. The only difference here, in the product, you have to consider liquid version of the water, liquid form of the water has been converted to the vapor. So what you need to consider at outlet, the heat of evaporation for water. So we have to add this heat of evaporation because this process has higher heat of reaction because of this actually change. So I added heat of evaporation of water to this value. And because it is 5 mole, I mean the stoichiometric coefficient is 5, we just multiply it by 5. And in the reactant part, you have N-butane that already converted to the liquid. So you have to consider minus form of evaporation heat for N-butane. That is why I put minus. As I mentioned, if the value is conversion is liquid to vapor, you have to consider the evaporation heat. If it is reverse form, I mean the gas to liquid, you have to consider reverse value of the evaporation heat of that component. This minus is because in delta H form, we consider H of product minus H of the reactant. So minus minus will be positive, and I calculate delta H of this reaction. As you have the delta H of the reaction, you just need the extent of the reaction that we just calculated. It is 2,400 of CO2 that is produced. There is no inlet CO2, so it will be an 4 is the stoichiometric coefficient. We calculate this and we substitute here by knowing the standard heat of reaction. We can calculate the rate of enthalpy change. So another example that we want to study here is the standard heat of the following combustion reactions have been determined experimentally. So we have 3 reactions. They ask us to use Hess law and to determine the standard heat of reaction for this reaction. So by using the Hess law, we have to use actually the known reaction to be able to calculate the standard heat of reaction for this reaction. I just provided for you what we have in this problem. We have actually ethane here, combustion of the ethane here, heat of reaction is provided. We have combustion of the carbon, and then hydrogen. So we have all the heat of reaction for this standard heat of reaction for these processes. What we are asked to calculate the heat of reaction for this process. As we go through this process, we need 2 mole of carbon. So that is a reaction that we are provided. They are provided for us. So we multiply this reaction by 2 to be able to provide the amount we need in this reaction. As we multiply the stoichiometric coefficient of this reaction by 2, we have to multiply the heat of reaction by 2 as well. So in the second part, we need 3 moles of hydrogen. Here we have the reaction that hydrogen is involved, which is actually 1. So we multiply this reaction by 3, the stoichiometric, 3, 3 half, and 3. So as we multiply it by 3, we have to multiply the standard heat of reaction by 3 as well. To be able to have ethane here, we have to go to the reaction involved with the ethane. So this reaction, we have to just flip it because here we have the ethane as the product, here is as a reactant. So I flipped this reaction. As we flip this reaction, we have to reverse the values of the heat of reaction. So we know by this 3 reaction, by adding these 3 reaction together, we can reach to the reaction with the, that is we actually willing to, our desired reaction, which is here. So since the addition of this reaction will lead to this reaction, we can add all this value now together and calculate this standard heat of reaction of this reaction by using his law. I hope it is clear. So now, so far we use other ways. We are given the heat of reaction, or we use other ways to calculate heat of reaction. There is another 2 ways we can calculate heat of reaction, which is from heat of combustion or heat of formation. So if you have a reaction like this reaction, and you have heat of formation of all the components of the reaction, I mean the reactant and product, you can use this equation to calculate the standard heat of reaction. So you have to consider heat of reaction, heat of formation, standard heat of formation of the product, which is multiplied by stoichiometric coefficient, minus heat of formation of the reactant. So you just need the heat of reaction of all the components of the product. Standard heat of formation of this. If you remember in the previous chapter when we studied table B1, I showed you that you have information of heat of formation, the standard heat of formation in table B1. So you can use those values in table B1 and consider the values you want and calculate the standard heat of reaction. You have to consider the standard heat of formation for all elemental species are 0, like H2, O2, N2. Moreover, if you want to calculate, both methods are available and you can use either of them. If you have the heat of combustion of all the components of a reaction, you have to use this equation to be able to calculate standard heat of reaction. The only difference between these 2 equations here, you have to consider delta H is equal to H reactants minus H products. So the same way, if you have the combustion or standard heat of combustion of all the elements, the only difference is H reactant minus H product. Again, these standard heat of combustion are available in table B1 in the textbook you have. And you have to consider that standard heat of combustion for any reactant or product like CO2, H2, SO2 are equal to 0 if they are combustion products. So that is the table B1 I wanted to show you. In table B1, these 2 columns will give you the These two columns will give you the heat of standard heat of formation and standard heat of combustion that you can use for different components. Now let's practice what we learned in some examples. So we have this reaction that we know oxygen is involved when there is a combustion reaction. So we have to use heat of combustion and heat of formation to determine the standard heat of reaction. So we want to compare both methods. If we use a standard heat of formation or we use a standard heat of combustion to calculate a standard heat of reaction. So what we see here, first of all, we have this reaction as we know. We refer to table B1 and read all the standard heat of formation of all the components involved in our reaction. So we have 1, 2, 3, 4 components. So we have to provide the standard heat of formation of all 4 components. So we have to refer to table B1. For the first component, we will find, sorry, here, it is the value that we can find in table B1. For the second component, this is O2. We know the standard heat of formation for O2 is 0. There is no energy for forming. There is no need for any energy to form O2 because it is available naturally as O2. So for CO2, we refer to the table and read, and the same for water. You have to consider when you are reading the data from the table, you have to consider the phase of each component when you are reading the data from the table. So as we know, we just have to put it in this equation that is a stoichiometric values multiplying by a standard heat of formation for product minus a stoichiometric value multiplying by a standard heat of formation for reactants. So that is why we put, you see, 1 multiplied by this value sorry, yeah. So we have 2 mole of CO2, so we have to, and 3 moles of water, so 3 moles of water, 3 stoichiometric coefficient of water is 3, the values of -3 plus 2 multiplied by the standard heat of formation of the CO2 minus the reactant, which is here. So that is the way that we calculate the standard heat of reaction from the standard heat of formation. Now, with the same reaction, we will calculate heat of reaction from heat of combustion. So here, this time, we go to the table and read the, sorry, here our combustion, it should be C. Let me, okay. So you have to, sorry, these values are C. It was a mistake on the typing. It's a typo error because it is heat of combustion. They're all C. So for heat of combustion, we know for CO2 and H2O, because they are, when they are product, combustion product, it should be considered 0. For O2, there is no heat of combustion, it is 0. And the only heat of combustion data we have here is for this component, that is -1366. So if you compare this value with the previous value, they are so close. So either you use heat of combustion, heat of formation method, or heat of combustion method, you reach to the same value for heat of reaction. So I give you actually 2 assignments here, so you just practice by yourself. We have another reaction here now. So you are supposed to calculate the standard heat of reaction for this process using heat of formation and heat of combustion method. So here I calculate for you from heat of formation. So by knowing heat of formation, we know we need heat of formation of CO2, heat of formation of water. We have to multiply by stoichiometric coefficient of these components minus heat of formation of the reactant. So we need for this component, that is N-pentane, and for O2 we know it is 0 value. So by knowing the heat of formation of all these 3 components, we can calculate heat of reaction. So now you have to go to the table and calculate delta H, or standard heat of reaction from a standard heat of combustion. So again, for this process, we just, this one are considered 0 as they are the product of the heat of combustion. So the only term that you have to read from the table is C5, N actually pentane. So if you go to the table, you will find the value is near to this value. So please refer to the table B1 and try to calculate heat of reaction from heat of combustion. And this is another example that you can try by yourself. So by giving you this introduction, you can actually pause this video, go and actually practice by yourself. This example I provided for you, try to do it by yourself. Just read the question and answer the question by yourself. If you have any problem, just come back to me for any more explanation or clarification. After this point, now we want to go to the main focus of this chapter. That is energy balance on reactive process. When there is a reaction involved in the process, how you have to do energy balance. First of all, a general procedure that you have to do, as always, you have to draw and label the flow chart. You have to draw the flow chart of the process and actually draw it and actually put all the information that you have. As usual, we have to do a material balance as we have the values of material balance, and as we can calculate, we have to do all of them and provide this value in the flow chart that we provided. We should actually provide the reference state for a specific enthalpy or internal energy. This reference state, as I told you in chapter 8, is a compulsory part of the process because you need a reference state to calculate the specific enthalpy or internal energy. After you provided this reference table, it is recommended that you provide the inlet outlet enthalpy table as we provided, and actually we practice now. And finally, as you have all the components that you provided this inlet outlet enthalpy table, you can easily calculate delta H or delta U, depends, and just put it in the final equation of energy balance and calculate the term that you need, if it is heat transfer or other terms that you may need. When you are doing the energy balance on a reactive process, you can either use, you have two methods for your calculation. You can use heat of reaction method or heat of formation method. We will practice both methods on one actually process. The difference between these two methods is the reference point. When you're using heat of reaction method, your reference point will be all actually reactant and product at 25 degrees and 1 atmosphere in the phase that they are existing in this temperature and pressure. For reactant and product, you have to use this reference point. For non-reactive components, you can use any reference point you want. Depends on you. Or even you can use this reference point. You will practice. While if you are using heat of formation method, you have to consider elemental species that constitute the reactant and product species at 25 degrees and 1 atmosphere as your reference point. What is that? Means carbon as solid, oxygen actually as a gas form, hydrogen as a gas form. They are the elemental species that are available in this condition at 25 degrees and 1 atmosphere. So both methods are applicable. Sometimes depends on the situation. One of them is easier to apply and the other one maybe is a bit more challenging, but you can use either two methods for your calculation of the energy balance on reactive processes. So let's start to understand, if you want to use heat of reaction method, what the steps we have to follow. So heat of reaction method, before we study about the steps, let's see how, in what condition is better we use heat of reaction method. Usually it is preferable for you to use this method when there is just one reaction involved in the process and a standard heat of reaction is known, or you can actually easily calculate it, as we just show you, different methods. So it is preferable right? So you can actually, that makes the calculation easier for you when there is just only one reaction involved and a standard heat of reaction is known, or you can easily calculate it. Sometimes it's not easy to calculate because the temperature of the inlet and outlet is not 25 degrees. We know we can calculate the standard heat of reaction only for 25 degrees. For other temperature, it's not easy to calculate. So if a standard heat of reaction is known, and if we just have one reaction involving process, it's better to select heat of reaction method. So what are steps you have to follow? As we always mention, you have to do a good material balance on the system whatsoever you have. You just provide the material balance with the known data, or if you can calculate, just add it. For sure, you have to draw the flow chart before this. Then you have to choose your reference state. Our reference state for heat of reaction method, as I mentioned, is clear. You have to consider all the reactant and products at 25 degrees and 1 atmosphere in the state they are available in this condition. So we know this temperature and pressure are the same temperature and pressure of the heat of reaction. That is why we use this point as the reference point. As you provided these two condition, or you follow these two steps, you have to calculate extent of reaction. Extent of reaction is easy to calculate. I show you. You can select any of the reactant or products that is available in. You have all the information of the inlet and outlet flow rate, molar flow rate or flow rate, and you can easily calculate extent of reaction. Then provide the inlet outlet enthalpy table and put all the values you have for material balance, for energy balance, all the value you have, put it in that table. And if you have any of the component at 25 and 1 atmosphere, you can select the enthalpy of that component 0 because it is the reference point. So after you provide this table, you know which component, actually the enthalpy, a specific enthalpy or a specific internal energy depends on the process, is unknown, and how you can calculate it based on the changes from the reference state and the information that you have, or tables and the process you have to employ. After you have all the information, it is easy to follow up. You can use, if you have single reaction, you can use this process, this actually equation. If you have multiple reaction, you can use this actually equation. So extent of reaction, standard heat of reaction, and all the actually this is a part we did in chapter 7 when there was no reaction. So the only difference that you have here, when you have reaction, you have to add it to the delta H equation. So this is actually you can get from the table that you provided and already calculated all the H involved in the system. Finally, you can just put the values of the delta H you have in this energy balance equation. That is for open system, for sure you have. For closed system, you know. So you can just substitute the values that you have, and if you want to calculate heat transfer or any other component that you want, you can easily calculate. For heat of actually formation method, this process, we use actually this method when we have multiple reactions, or when you have a single reaction, but the heat of reaction is not known, is not available. So you can use this method in that process. You will see, by actually going through the example, you will find out why it's easier. Same way, you have to start, you draw the flow chart, complete the material balance, and calculate all the material balance that you can provide in the flow chart. And then your reference state for heat of formation method is clear. You have to use elemental species that constitute the reactant and product in the state in which elements are found at 25 Celsius and 1 atmosphere, which is for carbon, it's solid form, for hydrogen, it's gas form, and actually for other O2 in gas form, hydrogen in gas form. These are the elements that found at 25 degree and 1 atmosphere. And you have to form those components involved in the reaction from these elements. So then you have to provide the inlet outlet enthalpy table and provide all the information you have, and then calculate, as we mentioned, you have to calculate a specific enthalpy. Here we are talking about open system, just for example. So you have to calculate all the specific enthalpy for the unknown problem. So I think it's better I show you in the example how you can provide this one. But as you learned so far, heat of formation at 25 degree and 1 atmosphere is available in the table. So means heat of formation, this heat of formation is when the specified elements are actually reacting together and form that specific component. So in table B1, you can read the heat of formation, standard heat of formation at 25 degree and 1 atmosphere. However, if the component available in your reaction have other temperature and pressure, you have to do further calculation to calculate those values. So you may use table B2, you may use table B8 or B9 in this way. We will explain how. At the end, you just can put in the simple equation that we have so far and calculate rate of enthalpy change. So we don't need, if you focus here, you will see we don't need a standard heat of reaction or heat of reaction in our calculation for heat of formation method. That is why we use this method, because it's not our concerned value. And at the end, as you have the values of delta H, you can put in the energy balance form and calculate what it is. If heat transfer or whatsoever you need, you can calculate. So now it's better to go through one example and see how we can do this energy balance on a reactive process by Bose method. So we have a reactor here in form of a furnace. We have some inlet streams, some outlet streams. So we want to see and we want to calculate the rate at which heat must be transferred to or from the reactor, assuming operation is done at, actually is happening at approximately 1 atmosphere. We want to use both heat of formation and heat of reaction method. For sure, when the reaction, you see, when we have our reaction and the standard heat of reaction is clear, we can use heat of reaction method. It is easier method, but I actually use both method for you to understand. So let's start. We want to use it from heat of reaction. So the first step I told you, provide the table. First of all, do all the material balance that you have in the system, and then provide the inlet outlet enthalpy table, right? So all the substance we have in this process, we just list it down. We have here so let me refer to a book. So we list down all the components involved in our process, which is C3H8 and C3H8, oxygen, nitrogen, water. So this is the component involved, all the components involved in our process. We just list them down. So So these are the all information we have, all the component we have. What we know in maybe all of them are not involved in the reaction, but anyway, we have to provide the information, all the substance we have to list them in the inlet outlet enthalpy table. So we have propane here, we have oxygen, we have nitrogen, we have carbon dioxide, we have hydrogen. These are all the components involved here. So then I provided all the information we have about material balance. So we have already is clear for us what is the molar flow rate, mole flow rate of each of the components. So we just substitute. These are the only three components involved in the inlet stream. That is why there is, if you can see here, there is no oxygen, there is no carbon dioxide, there is no water involved in the inlet stream. So I just put it dash without saying that there is no available. In the outlet stream, we don't have any propane, but other components are involved. So we just consider those components, oxygen, nitrogen, carbon dioxide, and water are all involved here. So we clearly know what is the temperature. Pressure is considered atmospheric from the problem. It's stated it is atmospheric pressure. So temperature is already clear for you. So for each of these components, you know what is the phase, what is the temperature, what is the pressure. So, and actually we don't have propane in the outlet. That is why we didn't consider here. It's important to know how to provide this table. It's very important. As long as we want to use heat of reaction method, we have to consider our reference is all the component we have in this reaction at 25 degree 1 atmosphere. At the phase, they are available in this temperature and pressure. We have some idea about some of the component at 25 degree and 1 atmosphere. Like for example, for propane, it is in gas form, for oxygen gas form, for nitrogen gas form, for carbon dioxide in this temperature and pressure, they are all gas, but water in this temperature and pressure is liquid. So we have to consider our reference at 20 degree 1 atmosphere, the phase, what is the phase of all the components that are involved in our process at 25 and 1 atmosphere. So it is not something we select by ourselves, it is something that existing in real situation at 25 degree and 1 atmosphere. So, but you have to know exactly the phase, the temperature and pressure of your reference point. So referring to this reference point, we can see this is 25 degree, 300 degree, 1000 degree. The only component here that is actually has the same temperature as the reference point is propane here. As long as this component is in the same reference, is existing at the same temperature of our reference point, we know for those components at reference point is a 0 enthalpy. So that is why we put 0 here, because propane in the process is actually available at 25 degree, which is our reference point. That is why we consider 0. The other are in different temperatures, so we have to calculate. The second point I asked you, the next step that I have to consider, we have to calculate the extent of reaction. So you can choose any of these components, I mean, between propane, oxygen, carbon dioxide, and water. You can use any of these components, of these 4 components, and calculate extent of reaction, because both inlet and outlet are clear. I'm just giving you an example. I selected propane here. You don't have propane in the outlet, so outlet is 0, inlet is 100, right? So divided by how much is the stoichiometric coefficient? 1, right? So it is 100. Okay, if you want to select oxygen, no issue. You have to mention 100 minus 500, means 500, divided stoichiometric coefficient of oxygen, which is 5. 500 divided by 5 is again 100. So I mean that if you choose any of these components, as long as inlet and outlet mole rate is clear, you can calculate and you reach to the same value. So extent of the reaction can be calculated from either of these 4 components, and they all should be same. So you can choose propane like me, you can choose oxygen, you can choose CO2, you can use water. You cannot use nitrogen because nitrogen is not involved in this reaction. So it should be for sure one of the reactive component, either from reactant or from products. But you have to put it in the same equation and calculate extent of reaction. Hope it's clear. So now we want to go through each of these specific enthalpy and calculate them. So we want to calculate H2. H2 is oxygen at 300 degrees. Oxygen 301 atmosphere. For all of them, you have to consider the changes from reference point, as we discussed before. So you have to consider reference point is oxygen at 25 and 1 atmosphere, and final state is oxygen at 301 atmosphere. This is what we have as H2. So for oxygen, this information, you can refer to table B8 at the end of your book. The specific enthalpies of some gases is available in this table. You have to consider, if you want to use this table, your reference state should be gas. For all of these components, they are gas at 25 degrees and 1 atmosphere, right? So if your component is not gas in this temperature and pressure, this table is not applicable. I think the only thing that you have to consider is water. You can use water only, you already considered this condition. I will explain to you. So this table is provided for you up to 1,500 degree is given to you. For sure there are atmospheric, there are Celsius, because it is 25 degree. And you see, at 25 degree, it considered the specific enthalpy is 0 because it is your reference point. So back to our calculation, we have from this to here, we know what is the specific enthalpy. We can read it from the table. For oxygen as 300, for oxygen at 300 is 8.79. For nitrogen is 8.12. For CO2, for water, for all of them is provided for you. That is why, that is how I read this value. H3 is nitrogen. H3 is nitrogen. What is the temperature here? 300 degrees. Again, we have to, if we have the specific enthalpy from this reference point for nitrogen, we can use it. That is why in this table B8, you can go to 300 for nitrogen and read the specific enthalpy. So that is where I read it for now H4. H4 is outlet stream. For oxygen outlet, what is the temperature? 1000. So here we have to read the specific enthalpy for oxygen and 1000 from the same table. Same goes to nitrogen here, H5, H6, and H7. H5 is nitrogen, H6 is CO2. These all information are available in table B8. The only one that affects us is water. Water at this reference point is at it is in liquid form. So for water, it is our reference point, water, 25 degree 1 atmosphere liquid. But what we have here, water at vapor, 1000 degree 1 atmosphere. For this one, we don't have available information in the table, so we have to choose the path that oxygen from here can be transferred to water from here can be transferred to water here. So we know that because the phase change, first we have to increase the temperature of the water in liquid form to 100, that is boiling point. Then we convert it at the same temperature and pressure to the gas or vapor form, then we can increase the temperature. So we have 3 changes of specific enthalpy here. So we have to add all these 3 together to calculate the specific enthalpy change here. So that is why here, as long as we have temperature change, while pressure is same, while the phase is same, we have to use CPDT, integration of 25 to 100 CPDT. Here there is evaporation heat from liquid to gas at 100 degrees. And the last one is again increasing the temperature at the same phase. Both are gas. Pressure is same, just temperature change from 100 to 1000 degrees. The only thing, CP information are available in table B2. You can read it from table B2. Delta HV is available in table B1 for water. CP again available in table B2. The only difference between this CP and this CP is this CP you have to find it for liquid, because in this stage water is liquid. This CP should be considered in gas phase. I have calculated these three values and find out that H7 here is 81.71. So now all the information are clear. We have all the values of specific enthalpy. We put it in the table. As we calculated, I put it in the table. Calculation now is easy because we already have extent of reaction. It's already provided for us what is the standard heat of reaction. And we have all the information of the mole flow of the outlet and inlet. So we have to add all the outlet together. So this one multiplied by this one plus this one multiplied by this, plus this one multiplied by this, plus this one multiplied by this, as I provided for you here, minus NI HI of the inlet that I just provided for you. So that will be delta H, changes rate of enthalpy change. Here in this process, Q is equal to delta H. So the same heat will be transferred from the system. As long as it is negative, means it is exothermic process. So this amount of the heat will be released from the reactor or furnace that we have. So that is the way we calculate. We use heat of reaction method. What if you want to use heat of formation method? So as you remember, in heat of formation, final equation of heat of formation, there is no heat of reaction involved. So we just need the changes of the specific enthalpy of all the components. But the only thing that matters here, what is our reference point or reference state? Our reference state, when we are using heat of formation method, is the elements, and these elements at the actually elemental situation when there is 25 degree 1 atmosphere. So for actually we have 4 components here involved. Propane, we have this information involved here. Propane, okay, there is no heat of formation for oxygen because it is available normally at 25 degrees as oxygen. For CO2, we have to see what is the heat of formation to form CO2 from carbon and oxygen. For H2O, you have to consider the heat of formation to form hydrogen from hydrogen and oxygen. So you have to consider all the elements that are available in this temperature and pressure. So as we want to start, so in this way, none of these points are in the reference point because our reference point is just elements. So this C38 in this 25 degree cannot be 0 because our reference point is not a component, it is just elements. So how you can consider, now how we can calculate? Your calculation has to consider standard heat of formation. For example, for H1, we have to know how C3H8 is formed from reference elements. For sure, it is carbon and hydrogen. Carbon and hydrogen together should react to form propane. So we have to know for formation of propane, how much energy is needed. We know we have a standard heat of formation of all elements, I mean most of the elements in table B1. So we need and we know what is the standard heat of formation for each of the elements that we need. For example, here we know what is the standard heat of formation for propane at 25 degree 1 atmosphere. Don't forget about this one. For oxygen, nitrogen, there is no heat of formation because they are actually as an element, they are available in the nature as oxygen and elements. So this H2O2, there is no need. I mean that there is no heat of formation to form O2 and nitrogen until 25 degree. I am talking about 25 degree and 1 atmosphere. After that, we have to explore the same way. So for all of these components, you have to consider first heat of formation and then consider their situation in the process. The first one we go through, we have to consider heat of formation for propane first, that we read from table 1 as this one. So we don't need to go further because the information that we need for propane is at 25 degree and 1 atmosphere. So that's it. We already calculated what is H1 because we just need to calculate heat of formation, or not calculate, read the heat of formation of propane at this temperature and pressure. Because propane in our process is at 25 degree, we don't need to go further because it's already reached to the point that we need. Now we go to the second H2, the H2, that is oxygen. In what condition? 300 degree. First of all, for oxygen, there is no heat of formation for 25 and 1 atmosphere because oxygen is available as oxygen O2 at this temperature and pressure. But what is the specific enthalpy from 25 atmosphere to 300? That is the condition of oxygen in our process. This one we have to consider. What is the energy needed to increase the temperature of oxygen from 25 to 300? You remember? We have this information. I mean, if it is your reference, if it want to reach to 300, we have in table B8. We can go and read what is the specific enthalpy of oxygen to reach to 300. The same thing goes to nitrogen. There is no heat of formation for nitrogen at 25 degree and 1 atmosphere, but to increase the temperature of nitrogen from 25 and 1 atmosphere to 300 degree, which is the temperature of the process, you have to go to table B8 and read the specific enthalpy of nitrogen at 300 degree. Again, in the outlet, you have oxygen at 1000 degree. So there is no heat of formation for oxygen for 25 degree, but to reach to 1000 degree, you need to read the specific heat of combustion, heat of the change from 25 degree to 1000 degree from table B8. So now we reach to H5, again is nitrogen at 1000. So for nitrogen at 1001 atmosphere, we know there is no heat of formation, but from 25 to 1000, we have to go to table. I just make it easier for you. From, we know delta H formation should be read from table B1. This temperature range has to be considered from other way. For us, for nitrogen, hydrogen, CO2, CO, water at gas form, from 25 degree to any other temperature, we can read it from table B8. For nitrogen to reach to 1000, this value is available in table B8. Now we reach to CO2 here. CO2 at 1001 atmosphere and gas form is the process that we have. We have to consider first heat of standard heat of formation of CO2 at 25 and 1 atmosphere. Then we consider how much energy we need to bring it to 1000 degree. So we have to refer to the table B1 and read what is the heat of formation of CO2 at 25 and 1 atmosphere, which I read. And then we table B8 and see for increasing the temperature of the CO2 from 25 that we read up to here to 1000, we can read this value from table B8. And we calculate the total amount of the specific enthalpy for CO2 at 1000 degree. And the last one is water. So we need water at 1001 atmosphere gas. So first we have to consider what is the heat of formation of water. So you can consider, that is actually in the table B1, there is two types of heat-off formation for water as gas, water as liquid. If we read water as gas, from here to here, we can use table B8 because water as gas, if a standard is water gas, we can use table B8, but if it is liquid, we cannot. So I read a standard heat-off formation for water at gas form from table B1 for water, and then use table B8, how to increase the temperature of water to 1000 from table B8. So it is not that much hard to calculate and to read most of them from the tables and data that we have. And I just read all the H that we want here. So the rest is easy. As you have all the values of H and N, you just have to put it here in this equation without needing to insert the heat of reaction process. And actually, in fact, it is already input. It's already inserted by the calculation we did. So I just put whatsoever, I just multiplied and add all this part in the outlet minus the inlet part and calculated the rate of enthalpy change, rate of enthalpy change. If you compare this value, minus 1.26 multiplied by 10 minus 5 and minus 126 multiplied, you see the values are not that much different. So by using either heat of formation method or heat of reaction method, values are not too much different. So you can use either of these two methods to read it, to calculate the or to do energy balance on reactive process. I hope that you understand the main concept of this week of study. Please refer to the material and actually try to follow the step by yourself and calculate it, and come to me if you have any problem or actually you need clarification. So I just provided one assignment for you here to actually try to learn what we have done so far on this problem. You can refer to your book for more examples in this regards. And these are the references that we use in our material. I wish you all the best. Have a great day. Take care. Bye.